Okay, so the second part of the fundamental theorem of calculus is what's going to be more useful for us when we're actually doing calculations on integrals. Because it actually gives us a way to do these calculations without having to take limits of Riemann sums. Right? And that's nice. You don't have to deal with the sigma notation anymore. And it turns out that in order to calculate an integral, right, in order to evaluate an integral, for instance, here we have the integral of f of x dx from a to b, the fundamental theorem says it suffices to find a function capital F that's an antiderivative of small f. And what does antiderivative mean? Well, it's basically the reverse of differentiation, right? So if you recall, x to the fourth power, its derivative is 4x cubed. We would then say that x to the fourth power is an antiderivative of 4x cubed. Right? It's whatever function you needed to start with to end up with small f as its derivative. Right? So the fundamental theorem says if you find such a function capital F, then you can just evaluate capital F at b, the upper limit, evaluate capital F at a, the lower limit, and subtract. And that's it. You've evaluated the integral. Right? And this is the exact value of that integral. Right? It's not an approximation. You don't have to take any other limits. And what's really impressive about this is that if you think about it, we're only really evaluating capital F here at the endpoints of your interval. Right? So if you had the graph of small f here, this integral corresponds to exactly this area here under the curve and above the x-axis. What this theorem tells us is that we only need to know the function value of capital F of x at the endpoints in order to get that area. Right? And so in my small example up here, well, since x to the fourth power is an antiderivative of 4x cubed, what that then tells me is if I draw the graph of 4x cubed and I wanted to take, say, the area under the curve from 0 to 2, then I would just need to evaluate the antiderivative x to the fourth power at 0 and 2. So the way we represent that is by putting a vertical line or a square parenthesis on the right, or a square bracket, and then write the 0 on the bottom and the 2 on top. And this means simply that we're plugging into the function x to the fourth power and plugging in 0 and subtracting, getting 16. Right? And so 16 here is the area under the curve of 4x cubed. Okay, so how about this one? Find the net signed area in between the curve of y equals 9 minus x squared, which is this parabola you see, and the x-axis from x equals 1 to x equals 4. Okay, so this is 1, 2, 3, and 4. What we're looking for is the net signed area representing basically this region here, whatever that area is, minus this region here below the x-axis from 3 to 4. Right, so remember that if you have a region that's below, that will correspond to a negative value. If you have a region that's above the x-axis, that corresponds to a positive value, when you evaluate the integral. And in fact, the net signed area can actually be evaluated by just taking the integral from 1 all the way to 4. Never mind that it crosses the x-axis there, right? Remember, so it's 9 minus x squared, the curve that we're looking at, dx. And by the fundamental theorem, right, the second part, it suffices here to find an antiderivative, right? So we ask the question, what function, when you take its derivative, gives you 9 minus x squared? Right, so what's in there? Well, the 9 is easy, right? So we know that 9x gives us 9, right? Because the derivative of the function a times x is just a, right? So we know that, so 9x becomes 9. How about x squared? Well, we know that differentiating polynomials brings their degree down by 1. So if you end up with x squared, that means originally you must have had an x cubed term, right? So that kind of makes sense because d dx of x cubed is equal to 3x squared, right? But we don't need 3x squared, we just need x squared, which means we need to divide by 3 so that we just get x squared as the result. So in fact, we need x cubed divided by 3 inside here. And now that's our antiderivative. So now I can write, well, this integral evaluates to 9x minus x cubed over 3. And we evaluated x equals 1 and x equals 4 and subtract the corresponding values to get the exact signed area. Right, so this is equal to 9 times 4 is 36. 4 cubed over 3, 64 over 3. And then you subtract the value you get when you plug in a 1. So it's 9 times 1 minus 1 over 3. And that's equal to 27 plus 21. Right, so 27 minus 21 is 6. Okay. Now, just to end here, I will make a note that if f is an antiderivative of small f, then capital F plus c is also an antiderivative for any real number c. Right? Because when you take the derivative of just a constant function, it just disappears. So in fact, I could have added a 5 here, for instance, inside my capital F function, and I take its derivative, I'm still going to get small f because the 5 just disappears. Right? And in terms of the calculation here for the integral, it doesn't matter. I can add a 5 in here, and well, that 5 is just going to cancel itself out of the calculation. Right? So in a sense, it says it doesn't really matter which antiderivative you take. There are infinitely many, right? Plug in any real number, you get one. Just take the simplest one. Throw it into your parenthesis, evaluate it in the lower limit and the upper limit, and you're done.